Hello everyone, myself Assistant Professor Vatsal D. Patel from Civil Engineering Department working at Mahatma Gandhi Institute of Technical Education and Research Center NAVSARI. Today we are going to discuss about trigonometric leveling. So be ready with your pen and paper. So first one is trigonometric leveling. Okay, so before we understand the trigonometric leveling, let us understand what is leveling. Okay, so leveling is a method of determining the relative heights, say elevation of various points. And in direct leveling, the difference of elevation is determined using leveling instrument, for example dumpy level, leveling staff, etc. Okay, but trigonometric leveling is indirect method of leveling. So in this method the relative heights, say elevations of various points, say objects, are determined from the vertical angle measured with a theodolite and horizontal distance measured with a tape. Okay, so you can see its arrangement in the figure. Okay, somewhat idea you will be getting from that. Okay, so if we talk about trigonometric leveling is not as accurate as direct leveling. It is generally used in topographic work and in very rugged terrain where direct leveling is difficult. It is commonly used in topographic work to find out the elevation of the top of buildings, temples, chimneys, church spires, and so on. So next is height and distances. Okay, so in this case, depending upon the horizontal distance between the station, it can be divided into following cases. Okay, so if the distance between instrument station and object is small, correction for earth curvature and refraction is not required. Whereas if the distance between instrument station and object is large, the combined correction is equal to 0.0673 d square for earth curvature and refraction is required, where capital D is equal to distance in kilometer. And if the vertical angle is positive, the correction is taken as positive, and if the vertical angle is negative, the correction is taken as negative. So depending upon the field conditions and the measurements that can be made with the instrument available, the following three cases are involved. Case 1, base of the object is accessible. Case 2, base of the object inaccessible and instrument stations are and the elevated object are in the same vertical plane. And case 3, base of the object inaccessible and instrument stations and the elevated object are in the same vertical plane. Okay, so these three cases are very important. Okay, so hope you concentrate on it because it is very useful for the examples in this particular module. Okay, so we will see each and every cases one by one. Okay, so let us start with the case 1. So first case is base of the object is accessible. So here you can see the image. Okay, arrangement will be there. Okay, so let it be assumed that the horizontal distance between the instrument and the object can be measured accurately. So let us consider a high object such as a chimney. Let us assume that the base A here, base A of the chimney is accessible. Okay, and the horizontal distance D here, we have already seen here horizontal distance capital D between the instrument station A and C can be measured using tape. Okay, so let us see what each and every term means. So here capital A is the instrument station, capital B is point to be observed. Okay, this one small h is the elevation of B from the instrument axis. Okay. Next, D, capital D here at the bottom, you can see horizontal distance between A and the base of the object. Next is here H1, this one, okay, this side. So it is the height of instrument, or say HI, capital HI, okay. Here BS, B suffix S, reading of star kept on benchmark. Here BM means benchmark, okay. And this one alpha is equal to angle of elevation, or say angle BAC, okay. So these are the main important terms, okay. So let us start with it, okay. So here I have listed out already each and every term, okay. So write down this one because it is important one, okay. So from the figure, H is equal to D tan alpha, which is we have to refer as equation 1, because we know that it is given by distance into height, okay. So from that equation is come H is equal to D tan alpha. Next, RL of B, so reduced level of point B, is equal to reduced level of benchmark plus BS plus small h, okay. So next what will be it? RL of benchmark plus BS plus D tan alpha, because we have get the value from here h, okay, from equation 1. So we are putting equation 1 value here h, value of h, and it's become equation 2, okay. Now when the distance between instrument station and object is large, then correction for earth curvature and refraction is required. As we start earlier, we already discussed this, okay. So combined correction will be 0.0673 d square, where d is equal to distance in kilometer, okay. So reduced level of B, or say RL of B, is equal to RL of benchmark plus BS plus D tan alpha, and the which correction which required we have added it, okay. So here only one term is added, which is combined correction 0.0673 d square, okay. So let us talk about correction for curvature and refraction. So it is according to this arrangement, okay, this all arrangement, and this will be different according to the distance between A and B, okay. So first of all, if we talk about if the distance between A and B is small sorry, so let us start with the if the distance between A and B is small, okay. So AB dash, this distance is equal to AC, this distance is equal to D here, all, okay. So AB dash is equal to AC is equal to D, all the values are same, okay. Next, angle ACB is equal to 90 degree. Similarly, BA dash, okay, BA dash is equal to BC dash, and already it is equal to capital D, okay, same value here, okay. So next condition will be BA dash is equal to BC dash is equal to D. Angle, which angle? AC dash B is 90 degree, okay. So we were getting the value of BC is equal to D tan alpha, and AC dash is equal to D tan beta according to the equation, okay, and according to the this arrangement, okay. So horizontal line, level line, all are shown here, okay, which are required for the correction. So if the distance between A and B is large, then the correction for earth curvature and refraction is required. Combined correction is equal to 0.0673 d square, where d is equal to distance in kilometer, okay. So the difference in elevation between A and B will be H is equal to BB dash, okay. So it will be given by BC plus CB dash, okay. So here what we are getting, BB dash, okay. So BB dash is equal to BC, this one, plus CB dash, C and B dash, this one, these two values summation, okay. So it will be given by d tan alpha plus 0.0673 d square, and we will term it as a equation number 1. Okay. Next, if the angle of depression B to A is measured, okay, B to A, okay, so AC dash is equal to D tan beta, where BC dash is equal to D, which already we have seen, okay. Next, the true difference in elevation between A and B, H is equal to A dash, okay. So it will be given by AC dash minus A dash C dash, okay. So equation will be D tan beta minus 0.0673 d square, and we will term it as equation number 2, okay. So if we talk about this one, okay, so A dash H is equal to A dash, and it is given by AC dash minus A dash C dash, okay. So it will be termed as equation 2. So next, adding equation 1 and 2, H is equal to D tan alpha plus D tan beta, okay. So H will be D by 2 into bracket tan alpha plus D tan beta, and we will term it as equation number 3, okay. So from equation 3, it can be seen that by reciprocal method of observation, the correction for earth curvature and refraction can be eliminated, okay. So RL of station B is equal to RL of station A plus H, okay. So we now have value of H, okay. So putting the value of H, so it is given by RL of station A plus D by 2 into bracket tan alpha plus D tan beta, okay, which is the required equation, okay. So these are the correction, okay. Next, case 2, base of the object inaccessible and instrument stations in the vertical plane as the elevated object. So this method is used when it is not possible to measure the horizontal distance capital D between the instrument station and the base of the object. In first case, we have seen that the distance can be measured, okay, but in this case distance cannot be measured, okay. So in this method, the instrument is set on the two different station and the observation of the object are taken, okay. So there may be two cases in this one, okay. First one, instrument axis at the same level, and second one, instrument axis at the different level. It is further divided into two parts. Height of instrument axis nearer to the object is lower, and height of instrument axis near to the object is higher, okay. So let us understand these all cases one by one, okay. So first one is instrument axis at the same level, okay. So here A and B, okay, this one A and B, okay, are the instrument station. Small h is equal to elevation of top of the object, here P, say top of the object is capital P, from the instrument axis, okay. Next, small b, this one here, okay, small b, okay, horizontal distance between A and B. Next, D, capital D, okay, at the bottom here you can see it, okay, horizontal distance between A and the base of the object. Alpha 1, this one, alpha 1, okay, alpha 1 is equal to angle of elevation from A to P, and alpha 2, this one, alpha 2 is equal to angle of elevation from B to P, okay. So I have already listed out this each and every term, okay, so you can write down it, okay. So let us start procedure. So from triangle, which triangle? Triangle P A dash P dash is equal, H1 is equal to D tan alpha 1, which is equation 1, okay. So if we talk about this one, okay, so triangle, which triangle we are taking? P A dash and P dash, okay, this triangle. So it is given by H1 D tan alpha 1, H1 is equal to D tan alpha 1, and same as triangle P B dash P H2 is equal to small b plus D and into tan alpha 2, and with it will be termed as equation number 2. Okay, so equating 1 and 2, d tan alpha 1 is equal to b plus d tan alpha 2. Okay, next it is the further procedure which you can easily do. Okay, so d tan alpha is equal to b tan alpha 2 plus d tan alpha 2. Next, d is equal to tan alpha 1, d into bracket tan alpha 1 minus tan alpha 2 is equal to b tan alpha 2. Okay, so now we will getting the value of d, which is b tan alpha 2 divided by tan alpha 1 minus tan alpha 2, and it is termed as equation number 3. Okay, so substitute the value of d in equation 1. Okay, so our equation 1 is d tan alpha 1, h1 is equal to d tan alpha 1. Okay, so from that equation we will getting d is equal to b tan alpha 1 tan alpha 2 divided by tan alpha 1 minus tan alpha 2, and it will be termed as equation number 4. Okay, so RL of P, okay, is equal to RL of benchmark plus BS plus H, which is the required equation. Okay, so these all theories are most important for the sum purpose. Okay, mainly. Okay, example purpose. Okay, so be sure you understand each and every equation and remember it. Okay, next, instrument axis at the different levels. In the field, it is very difficult to keep the same height of the instrument axis at different station. Okay, in previous case what we have done, we are not getting the value of d. Okay, directly measure distance d, so we have chosen the different station. Okay, and then the distance is getting by some procedure, but it is not possible to keep the same height of instrument axis at the different station. Okay, so therefore the instrument is set at two different stations, and the height of instrument axis in both the cases is determined by taking backside on benchmark. Okay, so there are two cases in this one also. Height of instrument axis nearer to the object is lower, and height of the instrument axis near to the object is higher. Lower and higher, two cases. Okay, so let us see height of the instrument axis nearer to the object is lower. Okay, so this is all the procedure, this is all the arrangement. Okay, so let us understand it. Okay, so first one, from triangle, same triangle, which one, p a dash p dash, and same as the equation h1 is equal to d tan alpha 1. Okay, so first we are taking the triangle p a dash and p dash. Okay, so and then equation is h1 is equal to d tan alpha 1, same as triangle p b dash p double dash. h2 is equal to b plus d tan alpha 2, and we will term it as equation number 2. So deducting equation 2 from equation 1, which is very easy. Okay, so h1 minus h2 is equal to d tan alpha 1 minus into bracket b plus d tan alpha 2. So it will be further simplified into d tan alpha 1 minus b tan alpha 2 minus capital D tan alpha 2. Okay, so now we know that HD is equal to h1 minus h2, so we can replace it. So HD is equal to d into bracket tan alpha 1 minus tan alpha 2 bracket over minus b tan alpha 2. Okay, so further simplifying the equation, HD plus d b tan alpha 2 is equal to d into bracket tan alpha 1 minus tan alpha 2. Okay, so further if we simplify it, d is equal to hd plus b tan alpha 2 divided by tan alpha 1 minus tan alpha 2, putting the value of hd. Okay, and d, so d is equal to b plus hd cot alpha 2 bracket over tan alpha 2 divided by tan alpha 1 minus tan alpha 2, which will be our equation number 3. So substitute the value of d in equation 1. So our equation 1 is h1 is equal to d tan alpha 1. So h1 is equal to b minus hd cot alpha 2 into tan alpha 2 divided by tan alpha 1 minus tan alpha 2, which will be our equation number 4. Okay, so these all are the cases. It is mainly important for the examples. Okay, so from this arrangement will be in the sums. Okay, so according to that equation are important, and we will solve an example with the help of this equation. Okay, so example point of view, these theories are important. Okay, next, height of the instrument axis near to the object is higher. Okay, so same procedure will be there. So from triangle p a dash p dash, h1 is given by d tan alpha 1, equation number 1. Triangle p b dash p double dash, h2 is equal to b plus d tan alpha 2, which will be equation number 2. So deducting equation 1 from equation 2, so h2 minus h1 is equal to b plus d tan alpha 2 minus d tan alpha 1. Further simplifying it, b tan alpha 2 plus d tan alpha 2 minus d tan alpha 1. Now we already know hd is equal to h1 minus h2, so hd will be b tan alpha 2 plus d into bracket tan alpha 2 minus tan alpha 1. So hd minus b tan alpha 2 is equal to d tan alpha 2 minus tan alpha 1. So minus hd plus b tan alpha 2 is equal to d into bracket tan alpha 1 minus tan alpha 2. Okay, so further same simplify the equation. So d is equal to b tan alpha 2 minus hd divided by tan alpha 1 minus tan alpha 2. Further we will get the value like d is equal to b minus hd cot alpha 2 into tan alpha 2 divided by tan alpha 1 minus tan alpha 2, which will be our equation number 3. Same, substitute the value of d in equation 1. So our equation 1 is h1 is equal to d tan alpha 1. So h1 will be b minus hd cot alpha 2 into tan alpha 1 tan alpha 2 divided by tan alpha 1 minus tan alpha 2, which is our equation number 4. Okay, so in about two cases, the equation of d, capital D, and h1 are d is equal to b plus n minus hd cot alpha 2 bracket over into tan alpha 2 divided by tan alpha 1 minus tan alpha 2, and h1 is equal to into bracket b plus n minus hd cot alpha 2 bracket over into tan alpha 1 tan alpha 2 divided by tan alpha 1 minus tan alpha 2. So use positive or say plus sign if a is lower. Okay, and use negative sign or say minus sign if a is higher. So this is the only main one. So these two equations are most important. Okay, these two are most important and this term is main. Okay, so according to it you can utilize it. Okay, according to the data. Next, case 3. So base of the object inaccessible, instrument stations not in the same vertical plane as the elevated object. Okay, so let A, this one A and B, the two instrument station not in the same vertical plane as that of P. Okay, so let us this one A and B, two instrument station not in the same vertical plane as of P. Okay, they are not in the same vertical plane. Okay, so what will be the procedure? Select two survey station A and B on the level ground and measure small b as the horizontal distance between them. Okay, set the instrument at A and level it accurately. Set the vernier to 0 degree. Bring the altitude level bubble at the center and take a backside say HS on the staff kept on benchmark. Okay, next is measure the angle of elevation say alpha 1 to P. Okay, this one alpha 1 to P. Okay, and measure the horizontal angle at A, say angle BAC is equal to theta. Okay, shift the instrument to B and measure the angle of elevation alpha 2 to P and measure the horizontal angle at B as alpha. Okay, so this all term. Okay, so let us see it in the image. Okay, so first of all alpha 1, this one alpha 1. So alpha 1 will be angle of elevation from A to P. Okay, next alpha 2, this one alpha 2, angle of elevation from B to P. Okay, theta, which is here. Okay, theta, 1 minute, theta. Okay, so theta is equal to horizontal angle, say angle BAC at station in clockwise direction. Okay, and alpha, this one alpha. Okay, horizontal angle, say angle CBA at station B in clockwise direction. Okay, so B is equal to horizontal distance between A and B. H1 is equal to P1. H1 will be this one. H1 is equal to P1. Okay, so height of object P from instrument axis of A, and H2 is equal to P2. Okay, this. Okay, so height of object P from instrument axis of B. Okay, so let us see the procedure. So all the terms are mentioned here. Okay, so note down all one. Okay, so in triangle ABC, angle BAC is equal to theta and angle ABC equal to alpha. Okay, so angle ACB is equal to 180 minus theta plus alpha, and as for the figure AB is equal to small b. Okay, so we know three angles and one side of triangle ABC. So therefore using sine rule we can calculate distance AC and BC as below, like BC is equal to B sine theta divided by sine into 180 minus theta plus alpha, and it is termed as equation number 1, and AC is equal to B sine alpha divided by sine into bracket 180 minus theta plus alpha, and we will note down it as a equation number 2. Okay, so now as we know H1 is equal to AC tan alpha 1 and H2 is equal to BC tan alpha 2. Okay, so values of AC and BC are obtained from the equation 1 and 2 as above. Okay, so RL of P will be height of instrument axis at A plus H1, or RL of P is equal to height of instrument axis at B plus H2. Okay, so height of instrument axis at A, station A, is equal to RL of benchmark plus BS. Okay, so BS is already we know HS, so RL of BM plus HS. Okay, and height of instrument axis at B is equal to RL of benchmark plus BS. So this is the required equation. Okay, so same, these are mainly important for the sum purpose or say example purpose. Okay, so write down each and every values, okay, or say equation. Okay, next topic is direct leveling on steep ground. Okay, so you can see its arrangement in the figure. Okay, steep ground is there. Okay, so if the ground is quite steep, okay, the method of indirect leveling can be used with advantage. Okay, so till now we have seen the different elevation and heights. Okay, and according to that we have derived the equation. Okay, now we will derive the equation for the steep ground. Okay, the ground is steep. Okay, so indirect leveling can also be used where ground is steeper. The procedure used to determine the difference elevation between A and B. Now we are going to see. Okay, so the following procedure can be used to determine the difference of elevation between P and R. Okay, so first of all, set up the instrument at convenience station O1 on the line PR. Okay, so this one, this is the line PR. Okay, steep ground over steep ground. So first procedure will be set up the instrument at convenience station, say O1. Okay, next make the line of collimation roughly parallel to the slope of the ground and clamp the telescope. Okay, so line of collimation will be here. Okay, so approximately we have to roughly parallel to the ground. Okay, next take a backside, say PP dash, this one, backside will be this one, PP dash. Okay, on the staff held at point P, and also measure the vertical angle alpha 1, this one alpha 1 at P dash. Okay, next determine the RL of P dash as RL of P dash equal to RL of P plus PP dash. Okay, so RL of P plus PP dash will be the our RL of P dash. Okay, next take a foresight. Okay, so this one Q q dash on the stab held as the turning point q, this one q, okay, without changing the vertical angle, okay, we have not changing the vertical angle is here second angle, okay, so angle is same, okay, so measure the slope distance p and q, this one p and q between p and q, okay, so RL of q is equal to RL of p dash plus pq sin alpha 1 minus qq dash, or RL of q is equal to RL of p plus pp dash plus pq sin alpha 1 minus qq dash, okay. Next, shift the instrument to the station O2 midway between Q and R, okay, between midway, not exactly in the mid, okay, midway anyway, okay, on it is not like that you put it in the middle, okay, so shift the instrument at the station O2 midway between Q and R, make the line of collimator parallel to the top of ground and clamp the telescope, okay, though it is already done, okay. So take a backside, say Q double dash on the stab held at the turning point Q. Measure the vertical angle alpha to this one, okay. So RL of Q double dash will be RL of Q plus Q double dash, okay. So take a foresight on R dash this one, okay, on the stab held at the point R without changing the vertical angle alpha to same, we are not changing the angle, and measure the sloping distance QR, this one QR, okay, sloping distance QR, okay, then RL of R will be RL of Q double dash plus QR sin alpha 2 minus RR dash. Thus, the RL of R is equal to into bracket RL of P plus PP dash plus PQ sin alpha 1 minus QQ dash bracket over plus QQ double dash plus QR sin alpha 2 minus RR dash bracket over. So, these are already written here all the procedure, okay. So, setup is here and we have derived which we understand in the figure is written here, okay. So note down each and everything, okay. This is the important one, okay. So this theory is important, okay. So we have already discussed all this one. So here are some important questions which can be asked in your examination, okay, and we have seen all this one, okay. So hope you understand it very clearly, and mainly these are mainly important for the examples, okay. So be sure you remember all the cases and according to that all the equation, okay. So here I end my session. Thank you all of you.